we have obtained canonical partition function and we define canonical partition function by Q, which is function of n, number of particles, volume, and beta is e to the minus beta Ej. Ej is function of number of particles and volume, where j is number of states. We have also obtained probability of jth state. We define it by Pj, which is also a function of n, v, and beta. Is e to the minus beta Ej n v by q. Since we have obtained partition function as well as the probability, now we can calculate all the thermodynamic quantities like average energy, and we define average energy by this. Okay. So, what is the average energy? Average energy E is sum over j Pj, which is function of Nv beta times Ej, which is a function of N and V. If you remember, the probability of any variable x is like sum over j xj times pj. We already discussed this. Is very similar to this. Now, if we substitute the value of probability pj, we obtain so, this is the expression we obtain for average energy. So, average energy is sum over j e to the minus beta Ej times Ej by q. Now, if we closely look at the expression for partition function as well as the expression 1, we see that in the denominator we have q, okay, and in the numerator we have sum over j e to the minus beta Ej times Ej. So, it says that we need to take log of q first, and then we need to differentiate q with respect to beta. Then what we get is like very similar to expression 1. Let us see. Okay, so, we have q now we take log e base q now we will differentiate ln q with respect to beta, keeping number of particles and volume constant, what we get. So, we are differentiating ln q with respect to beta. So, in the numerator we will have sum over j e to the minus beta ej, okay, and in the numerator we have sum over j e to the minus beta ej times minus ej. Now, if we compare expression 1 and expression 2, we obtain, so comparing equations 1 and 2, we get average energy is minus del ln q by del beta. At constant n and v. So, this is the expression for average energy. So, if we know the partition function, we can easily calculate average energy, and this average energy is nothing but the internal energy that we have used in classical thermodynamics. Now, we will see rather we will prove also that beta is 1 by kV times T, where kV and T is the absolute temperature. So, this is the expression for beta, okay, and we have obtained that average energy is minus del ln q n v beta by del beta at constant n and v. So, in terms of temperature, we can write average energy E is kB T to the 2 So, we obtain average energy is minus del ln q by del beta, and if we differentiate with respect to T, then we get the expression for average energy as kB T to the 2 del ln q by del T. So, this is the expression for average energy. Okay. Now, we will calculate average pressure. Since we are dealing with canonical partition function, in canonical partition function, number of particles, volume and temperature fixed, so pressure can fluctuate. So, we will calculate average pressure. To do this, we will start with the expression for average energy. Okay. Just now we have seen average energy, which is nothing but internal energy we can write like sum over j is number of states, Pj times Ej. So, we can further proceed like this, du like this. Okay. Then you can, this above expression can be reduced further to so suppose this is our expression number 3. Okay. So, here in expression 3 we have some over j p j del E j by del V at constant n. Since E is function of E j is function of n and V, we are differentiating with respect to V, keeping n constant, times dV and some over j E j times dPj. Okay. Now, if we compare, so from thermodynamics, okay, so we know du is del W plus del Q. And if the process is a reversible one, you can write del W reversible and del Q reversible. Okay. And we can further proceed and write, we know del W is minus P times dV plus del Q reversible. Now, if we compare, so suppose this is our equation 4. So, if you compare the coefficients of dV of equation 3 and 4, what we obtained is Pj is minus del Ej by del V at constant gain. This is because average pressure we can also write like sum over J probability of jth state times pressure at jth state. Okay. Now, if you compare this expression, suppose this is our expression 5. So, if you compare expression 5 and expression 3, okay, so you can write that Pj or pressure at the in the jth state is nothing but minus del Ej by del V. Okay. So, we obtain, so we know pressure, average pressure is sum over J where small p denotes probability and the capital P represents pressure. Now, we know the expression for probability. Okay. Now, if you substitute the expression for probability here, we get e to the minus beta Ej times Pj. So, Pj is again our minus del Ej by del V at constant n by Q. Okay. Now, we know Q is nothing but sum over j e to the minus beta e j. Now, what we will do, we will take log like before, log of q is like this. So, what we will do now, we will differentiate ln q with respect to v, keeping n and beta constant. Okay. So, if we do that, we get, from there we get del ln q by del v, keeping n and beta constant. So, we get 1 by q times sum over j e to the minus beta e j times minus beta del e j by del v at constant n. Okay. So, we get average pressure is nothing but minus, or if we substitute the value of beta, we get kBt del ln q by del v, keeping n and beta constant. Okay, so this is the expression for average pressure. Okay. Next, we have, so far we have assumed that beta is 1 by kBt. We will prove it now. Okay. So, next is proof of beta is 1 by kBt. Okay. So, we will start with average pressure. So, we know, we just discussed about the average pressure. Average pressure is nothing but Pj times Ej, and it is nothing but sum over j Ej is function of n and v e to the minus beta Ej by q. So, q is nothing but e to the minus beta Ej b. Okay. So, this is the value of average pressure. Now, what we will do, we will differentiate average pressure with respect to volume, keeping n and beta constant. So, if we do that, we get now, if we see right hand side, we have three functions which are functions of volume, like Ej, we have so Ej NV is our first function, e to the minus beta Ej is our second function, and sum over j e to the minus beta Ej that is present in the denominator, this is our third function. So, if we differentiate this, we will get So, we are differentiating the first function means Ej with respect to V. If we do that, we get this expression. Next, we will differentiate with e to the minus beta Ej with respect to volume. If we do that, we get Ej NV, this is unchanged, and then e to the minus beta Ej n times V times minus beta times del Ej by del V at constant n by sum over j e to the minus beta Ej. Now, we differentiate the denominator with respect to volume. If we do that, we get minus okay. So, this is the expression we obtain. Okay. So, we can further simplify this one. Now, if we look at the first term, what do we get? So, the first term gives you minus of average pressure. So, the first term gives, so what we get is del E by del V at constant n and beta. The first term gives us average pressure. Okay. Now, the second term. Okay. If we see the second term, okay, so we have one beta term there. So, we have plus beta, we can take beta out, and then if we take the minus sign in minus del Ej by del V, so we get Pj, right, pressure. Okay. So, we get average of pressure times energy, the second term gives. And the third term, now if we look at the third term, the first term gives us the average energy. Now, if we split, only when if we split the denominator into two different sum of j e to the minus beta Ej term. Okay. So, if we do that, basically we get, so the first term gives you minus is there. So, you get, we get the first term gives us the average energy minus E average, and the second term gives us pressure. Okay, so minus average minus P average. So, what we get is, and then we have one beta term also there. So, one beta term is, one beta is also there. So, times beta times beta. So, this is the expression we have got if we differentiate average energy with respect to volume. Okay. So, we can write del E average by del V in beta is minus P average plus beta P times E average minus beta E average times P average. Now, for those who did not understand how we arrived at this expression, so we will I'll just show those things there. Okay. So now we consider, you go back and check the expression of this. So we if we see the first expression. Okay. So first in the above expression, suppose this is our equation. What is the equation? So this is our equation 6. So in equation 6, the first term is equation 6, the first term in the right hand side we have sum over j del Ej by del V times e to the minus beta Ej by e to the sum over j e to the minus beta Ej. Okay, so this term gives us Pj, average probability. Okay, so this term reduces to sum over j del Ej by del V at constant n times Pj. Okay, and this is nothing but average minus of average pressure. Okay, so this is the first term in the right hand side of equation 1. Now we consider the second term of equation 1. Okay, so the second term in the above expression 6, the second term in the right hand side of equation 6, what we have, sum over j Ej e to the minus beta Ej, and then we have times minus beta, and then times del Ej by del V at constant n, and then we have q. Okay, or rather we have sum over j e to the minus beta Ej. Now if we see, okay, so if we further reduce this one, so we can take, first we take beta out, okay, and then what we do here, we write Ej and then we have times minus del Ej by del V at constant n, and then we have e to the minus beta Ej by sum over j e to the minus beta Ej. So this term, this whole thing, this term is again nothing but probability. So, we can write this as sum over j E j, and this is nothing but pressure at jth state, and then we have probability of jth state. So, the whole thing is nothing but your variable now. So, we can write beta times P E average. So, this is the second term of equation 6 that is present in the right hand side. Now, what about the last term or third term? Okay. The third term in the expression 6 is E j. So, the third term of equation 6 present in the right hand side okay. So, we can write minus we can just forget time being. So, we can write E j e to the minus beta E j. So, sum over j E j e to the minus beta E j by sum over j e to the minus beta E j to the 2 times sum over j, and we have e to the minus beta E j times minus beta e to the minus beta E j times minus beta times del E j by del V at constant n. So, this is our third term of equation 6 that is present in the right hand side. Okay. Now, we can simplify this one like, so we can write j E j e to the minus beta E j by sum over j beta E j times beta we can take out, and then we can write j e to the minus beta E j minus of times minus of del E j by del V at constant n by sum over j e to the minus beta E j. Okay, so, the first term here gives E j times P j, and the second term gives us pressure P j times P j. So, this gives us beta E average times P average. So, that is how we arrived at equation 7. Okay. So, we name this one as equation 7. Okay. Now, what we do? We differentiate, we consider first, now we consider average pressure, and we will differentiate pressure with respect to beta. Okay. So, if we do that, we get, so we start with average pressure. So, we know average pressure is nothing but sum over j P j probability times pressure at jth state. Now, we substitute the value of P j here, and we get So, this is the value of average pressure. Now, we will differentiate average pressure with respect to beta, keeping N and V constant. Okay. So, if we do that, so we get so if you further simplify this expression, we get del P average by del beta at constant N and V, nothing but E P average plus P average times E average. Okay, so the first term gives you first term of right hand side gives you EP average, and the second term of right hand side gives you P average times E average. So, suppose this is our equation number 8. Okay, very good. Now, we will substitute the value of dP by del beta of equation 8 into equation 7. Okay. So, if we do this, what we get is, so from equation 7 and 8, so from equations 7 and 8, we get del E by del V at constant N and beta plus beta times del P average by del beta is minus P average. So, this is our equation 9, suppose this is our equation 9. Okay. So, again from thermodynamics we know, from first law of thermodynamics, we know dU is TdS minus PdV, right, that we discussed. Now, what we do? We differentiate these with respect to V, keeping temperature constant. We get del S by del V, du by del U by del V at constant temperature is nothing but T times del S by del V at constant temperature minus P. Okay. So, we get del U by del V minus T del S by del V at constant T is minus P. Again, del S by del V at constant temperature is nothing but del P by del T at constant volume. So, this is one of the Maxwell's relation. So, our equation 10 reduces to, so equation 10 now becomes, so equation 10 becomes del u by del v at constant temperature minus T del P by del T at constant volume is minus of pressure. So, this is our equation 11. Suppose this is our equation 11. Now, if we compare equation 11 and equation 9, so comparing equations 9 and equations 11, we get beta is proportional to 1 by T. Okay. And it has been found that the proportionality constant is nothing but Boltzmann constant. Okay. The constant, the proportionality constant turns out to be 1 by kb, okay, by comparison with expressions for the average energy or average pressure with known thermodynamic equations. Okay. So, we get, so beta is 1 by Boltzmann constant times temperature. So, we have proved that. So, next we consider, okay, what is the value of entropy. Okay. So, we calculate, now we consider calculation of entropy. Calculation of entropy. Okay. Suppose we are considering a function where f is nothing but log of partition function. Okay. So, f function of e1, e2, etc. is ln, and what is the value of q that we know? Q is nothing but sum over j e to the minus beta ej. Okay. So, we can write df is del f by del beta keeping n or keeping e1, e2, etc. constant. Okay. Because e1, e2, those terms they contain n and p. Okay. So, we can write e1, e2, etc. constants here. So, we are differentiating f with respect to beta, keeping e1, e2, etc. constant, time d beta plus, yes, plus sum over k, you can write del F by del Ek right. So, here del F by k is again a dummy variable. Okay. So, del F by del Ek beta u1 e2 etc. So, we are keeping beta u1 e2 etc. constant except the term Ek here. Okay. So, this is our equation 1 and this is our equation 2. And what is the first term? First term is our minus of E average. Okay. And what is the second term? Second term is, so this is nothing but minus E average and we have the d beta term. So, we have minus E average times d beta and the second term gives us minus beta sum over j pj times dpj. Okay. And then we get, so d f beta times E average, we can further simplify this one like this is beta times dE average minus sum over j pj dpj. Okay, so we get d f plus beta E average equals to beta dE average minus, and this is nothing but du. So, we discussed, so average of energy is nothing but internal energy minus del W. If the process is reversible one, we can write like this. Okay. So, we get d a plus beta E average is nothing but beta del Q reversible, or we can write del Q reversible by Kb times T. Now, we know del Q reversible by T gives you ds. So, you can write K beta times d a plus beta E average is nothing but ds. So, if you do the integration, we get S is Kb times F plus E average by T plus a constant term. Okay. And what is the value of F? F now, if we substitute the value of F, we get Kb ln Q plus E average by T plus constant. So, this is the value of average entropy. Now, we are more interested into difference in entropy rather than absolute entropy. Okay. So, we can safely ignore the constant term. So, if we ignore the constant term, we get S is Kb ln Q plus E by T. Okay. This is because we are more interested into difference in entropy or ds rather than absolute entropy. Okay. Now, we have obtained so far average energy, average pressure and entropy value. Now, we can calculate basically all thermodynamic quantities like like calculation of enthalpy. So, we know enthalpy H is U minus PV, and we know value of U. So, U is nothing but minus del ln Q by del T if we differentiate with respect to T. Then we do not have the minus sign, we have Kb times T to the 2, keeping N and V constant, and then the value of pressure we know is minus of kBT. Okay, so pressure, the value of average pressure is we just calculated. Okay, so value of average pressure is kBT. Okay, so minus del ln Q by del ln V you can write. Okay, because if we take the V in the denominator, we get this. Okay, this is at constant N and beta. And we can calculate Helmholtz free energy. Because A is nothing but U minus Ts, okay, and we substitute all the values here. So, U is nothing but Kb times T to the 2, or we can write Q U intact here. Okay, so, U minus T, and the value of S is Kbt, Kb ln Q, and then minus U. So, we get A is minus of Kbt ln Q. Similarly, we can calculate, we can also calculate Gibbs free energy. G, like G is H minus Ts, and we will substitute the value of H at S here by substituting the values of H and S. Okay, so basically we can calculate all thermodynamic quantities if we know the partition function. Thank you.